Hello students, I'm going to make a relatively short video on trig integrals. This is an essential piece of integration. It's a class of things we can do. It is sort of a special case. It's when you're integrating combinations of trig functions. I'm thinking of this video as a chance for me to give a refresher for students that have seen it before. So this is definitely part of our Calculus 2 course, but it comes up again in Calculus 3, the moment that we're using polar coordinates to do a double integral. And oftentimes people maybe don't remember the key ideas, or they remember it as this long list of things, which is really not the way to remember it. There is a table that says do this, do this. That's certainly not the way I remember it. Basically, this method is substitution except for one special case. So I'm going to tell you how I think about it. This is from one of my review sheets. And if you do a Google search for Andy Lovelace, of all the Andy Lovelace in the world, I have the biggest website. You can see all lecture notes where I do this. I have this summary page. This is from my Math 125 materials. And I have examples on there. But let me give you the quick version for somebody that's trying to do a refresher. Okay, so let's zoom out a little bit here. And I'm basically going to focus, and I would say the vast majority of the time when you use this, it's because you're doing sine and cosine. By far the most common. So I'll focus this discussion on that because that's all you're going to see in our Calculus 3 course. But the technique also works for tangent and secant. You kind of get that for free because it's the same idea. So here's what I mean. If there's an odd power anywhere, and you're dealing with just sine and cosine only and nothing else. So something like cosine to the third of x, there's an odd power. Something like sine to the fourth of x, that's even. And then cosine to the first. Okay, there's an odd power there. It works also if they're both odd. If you had a sine to the third, cosine to the fifth. So same technique, if one of them is odd, it's a substitution problem. So this does require you have a little bit of understanding with substitution. Maybe in the future I'll have a substitution video as well. But for now, we're setting up substitution. When you're dealing with sine and cosine, there's essentially two main options. One is to use cosine, the other is to use sine. And the entire technique is to try to make one of these work. But if you know about substitution, the only way it's going to work is if the derivative also appears. This is exactly how I think through it. So I basically just, in my head, I don't usually write this, but I go, okay, if there's an odd power, I'm going to either make this work or this work. And you basically can always make it work if there's an odd power, and you just need one trig identity. And that one trig identity is a trig identity everyone must know, which is that sine squared of x plus cosine squared of x equals 1. And the way we use this is we either solve for sine squared or cosine squared. This gives us a way, if the power is even, to go between the functions. Let me show you what I mean. So this one is already ready for substitution. Nothing has to be done. Why do I say it's already ready for substitution? You should be able to see that this problem was set up, and I was just randomly writing things down, but right here I already see this derivative, and everything over here involves sine. This is already ready to go. I don't need to do anything else. I just can write the integral of u to the fourth du, and then I will be done. I do 1/5 u to the fifth plus c. I replace it 1/5. So this is the main method. There is one special case which we have to talk about, and that's the case when you don't have this, but I'm going to do that next in the second part of this video. So if there is an odd power anywhere, this will always work. What do you mean it will always work? This doesn't look like a substitution. Let's go through and talk about that one. So in this one, there's an odd power. Here's the strategy. We're going to try to make this appear or this appear, whichever looks like it's the easiest. Well, in this case, there's only cosines. So step one is to rewrite the problem as if one of the cosines was out here. Aha, now we're setting up a substitution. But what happens when you subtract 1 from cosine to the third? And the other thing I should say, I find sometimes that just the notation bothers students. Cosine to the third means cosine times cosine times cosine. So if you take 1 out, there are 2 left. And so this is cosine squared. Now the problem this time is it's not perfectly set up. Because if you look over here, they are not sines like this one was. So I'm trying to do the substitution because I found this cosine, but I need everything else to be a sine, and that's when you use this identity. You say cosine is 1 minus sine squared, so you write the integral, 1 minus sine squared. So it's all this is clever substitution, and we can always do it. So you can have a long list of what to do if cosine's odd, what to do if sine's odd, what to do if they're both odd, but it's all the same idea. Then we're ready to go. This is the integral of 1 minus u squared du. Done. And then keep integrating. I shouldn't say done. So that's the idea. If there's an odd power anywhere, pull 1 out and then set up the rest for substitution. Now if I was going to go in more detail, here's one where they're both odd, so either one works, but the truth is it's probably a little easier to take out the one that has a smaller number because then you'll have less to change. Let me show you what I mean by that. So I'm going to take out one of the sines, and I don't think, if you're in Math 126 and using this video, I don't think you'll see anything this big, but in principle this works. So I factored out one of the sines, and now you can see I'm setting up to use the other one. Now the one catch on this one is there's a negative. That's not a big deal. You can either move the negative to the other side, but it is something you have to remember. So this right here is actually negative du, negative 1 times du, if you think about what this is. Okay, so now I'm trying to turn the rest of the problem into cosines. And some of it's already there. I can just write this as u to the 5th. But the question is, what can I do with this one? All right, so this one I can do the same thing. Use the same identity. This is 1 minus cosine squared. So usually when I do this myself, I don't even write that step. And then I'm ready to go. So this is negative. The integral I probably distribute, u to the 5th minus u to the 7th du. Compute, done. So that's that idea. So I give in my notes, I give several examples, but you need that plan of attack. Okay, a few little comments here. So I was hoping that this video was born out of helping someone today in office hours. In office hours, they were doing a double integral, and they ultimately had to do, if I can say this, they ultimately had to do the integral of cosine squared of x sine of x. And they didn't know what to do. And the answer to that was just a straight substitution. U equals cosine of x, and you'll be done quickly. I think in one homework question there's a cosine cubed. Again, we've done that one. Okay, so what happens if all the powers are even? So let's run that scenario. So what happens if you have the integral of sine squared of x, or the integral of cosine squared of x, or the integral of sine to the 4th of x? Well, then the same strategy doesn't work very well, and the reason it doesn't work very well, if you're curious, is after you pull out the sine, that square identity doesn't work very well over here, because sine squared of x is 1 minus cosine squared of x. Now you can take the square root, but then that gives you a messy integral, and it's no better than what you started with. So that's no good. So this is the hole in the method. And unfortunately, these are important. They come up a lot. So there's a technique, you use the half angle identities, and you can pretty much get away with just these two. 1/2, 1 minus. Some people call these the double angle identity. It depends on which side you're looking from. I'm not too picky about what we call it, but I do know some instructors are pickier about using the right language here. Okay, that's it. this is the workaround that people have discovered is kind of one of the fastest ways to deal with these in a universal way. So what you do is you just replace this with 1/2 1 minus cosine of 2x dx, and then the integral is fairly quick. So it's 1/2, and then it's the integral of this minus the integral of this, and both of those are in my table of integrals. This one you have to remember that it's 1/2 sine of 2x plus c, and that comes up a lot. So similarly, this is almost the exact same thing. There's a 1/2 1 plus cosine of 2x dx, and so this ends up being 1/2 x plus 1/2 sine of 2x plus c. And then lastly, what if it's a 4? You just keep banging it over the head with the half angle identity until the answer pops out. So this means there's 2 sine squared. So you basically write this identity twice. And this will work. It's a little bit longer, but you just keep going until the answer pops out. What do I mean by that? So you can factor out a 4th, and then we're going to expand this out. So it's 1 minus 2 cosine of 2x plus cosine squared of 2x, and that's this times this times this. There's our monkey face. That's what that looks like. Okay. At that point, we now have 2 integrals we know. This one is x. This one we know how to do. It's 2 times 1/2 sine of 2x. But this one we don't know how to do because it has an even power. So you keep banging it over the head of the half angle identity until the answer pops out. So let's do that. Let's keep going. This is 1/2. And at this point, you could integrate those. I tend to wait until I've completely simplified all these. There is a moment here where students tend to make mistakes, so I'm going to leave that blank for a second. The identity says that cosine squared of theta is 1/2 1 plus cosine of 2 theta. But you got to be careful in using the identity. If you replace theta with something else, here, let me erase this, you have to replace this theta with something else. So in this particular problem, this was 2x, and so there would be a 2x here, which means it's going to be a 4x. That's usually the part people mess up. And then we're ready to go. If I was doing this problem, I would simplify it. I would say there's a 1 here, there's a 1/2 here, that's 3/2 cosine of 2x, and there's still this 1/2 plus 1/2. Phew, we did it. It's not elegant, it just works. And then we're ready to go. So this is going to be 1/4, 3/2 x. Let's see, minus 2 times a half. Normally I would just cancel as I went. 2x plus 1/2, and there's a 1/4 sine of 4x plus c. That's it. So it's not pretty, but it's doable. We can do every combination of sine and cosine. If there's an odd anywhere, we do a substitution. If everything is even, we keep using the half angle identity. That's the method we teach in our Maths 125 class. In doing so, we talk about secant and tangent because it's the same squared identity, just written in a different way. And we talk about when can we set up a substitution there. And in doing that, we sort of broaden the method a little bit. But this just is one group of things we can do. If you give me a situation that involves sines and cosines, I can integrate it by using these couple strategies. There's of course special cases, and we do that in our in that course. Okay, hope that's interesting to you. Again, now I hope you at least have this idea. If you don't have to memorize it, basically the answer is substitution. So the method is you're going to do a substitution if there's an odd power of sine and cosine. In order to do the substitution, you're going to have to pull one term out from the odd power and use this identity. If they're both even, you're just going to bang it over the head with the half angle identity until the answer pops out. That's it. Hope that helps.